All right, so let's start our first class actually for this advanced finite element course. We're going to be looking at elastostatics in one dimension. I said a few minutes ago that everything that we're going to do first is in 1D. And we do so because even though it's not so interesting, right, the world is not one-dimensional, the concepts that we're going to find out in one-dimensional actually extend to 2 or 3 dimensions. So everything that we're going to see in 1D nicely extrapolates to the rest that we're going to be doing. So elastostatics in 1D, we're going to do first the strong form of the boundary value problem. We're going to do the weak form, the Galerkin form, and then we're going to take it from there. Okay. So what I draw here is basically a bar. So it's a 1D structural element that can only take what? We can only have axial forces, tension, and compression, right? So we're going to see that. Well, let's put some symbols. A is going to be the area. Then B is our load per unit length. Then we are going to assume that this bar is actually constrained laterally, right? So if you see here, I draw this point here, this little point, and it's basically constrained laterally with some spring that I assign a constant S. Basically, what this is going to do, if the bar starts moving in one direction, that spring is actually going to exert a force in the opposite direction. Okay? And although this is not very useful now, well, there are problems for which this is actually useful. Like, for instance, if you have some foundation, right, and the foundation is constrained laterally, and therefore you have some force that goes opposite to the movement. So we're going to call that S, where it's going to be our distributed spring. Then we're going to have E is our modulus of elasticity, or Young's modulus. And that's it. Well, the length of the bar is L, and then we're going to look at the equilibrium of an infinitesimal segment of that bar, delta x, as you can see here, and then we're going to see what are the forces that are applying to that to get our differential equation. So that is the first step. After that, we're going to see what are the boundary conditions. Okay. Now, normally, and this is something that you will find in papers, what we say is, well, the bar is basically omega. That's a symbol we normally give to a body, right? And this is a subset. So this symbol here is subset of the real line, right? So that basically means that I take a portion of the real line, and this is going to be where my bar exists. And then what we also say is we're defining the boundary of that bar. So the endpoints of that bar are basically going to be omega over bar minus omega. Omega over bar is basically some notation that basically means that you have the bar plus the endpoints, right? In terms of sets, this is basically saying the closure of a set. So normally omega is an open set. That basically means everything but the end nodes, right? And then the overline or overbar means that you're also considering the endpoints. So naturally, well, how do you define the boundary? Well, omega, the closure of the set, minus the open set gives you the boundary. And we are not going to get very mathematical or very technical in this course, but I really want to give you some little remarks like this every now and then that are important for you to really learn, because then when you are reading a paper, right, if you are going to follow a project, for instance, with finite elements or something like that, or topology optimization, as was asked earlier, then these are things that are important to know or to understand. Okay? Yeah.
So what does omega represent exactly? Is it location in the bar? Or
Omega is the whole bar.
the whole bar?
Yeah. Exactly. And then x is going to be the coordinate along the location along the bar. Yeah.
And the slash, so the omega.
Yeah. So that is this slash means set minus. So it's subtraction between two sets. I could have also written just a minus, but in some papers you have that slash, and that is basically a set minus another set. Okay? Okay, so if you look at this infinitesimal length, so what are the forces that are acting on that? Yeah? So you have some axial force that we call N, right? So I'm going to put here N is our axial force. We also see that we have the body force, so N was the only one remaining. So now if we're doing equilibrium of that infinitesimal this is our equilibrium. So sum of forces in the x direction equal to 0. And what you can see here is first we have the first term is basically this force that you have here, right? So you can see that there is some variation. So the actual force at n plus delta x doesn't have to be the same as the actual force at n of x, clearly. Then you're going to have some, this arrow is in the wrong direction, right? Because everything is in 1D. So we're going to have some load per unit length, but of course it has to apply. It has to be applied in the axial direction. So that's a mistake, and that's because we're used to write some gravity forces. Okay, but that is the direction of the load per unit length, and we assume that to be positive. That's why we have that sign here. And then the other one, as I said, this spring that is preventing the bar from moving in the positive direction is actually exerting a force opposite to it, right?
So what's it S U AX, the final term of the equation?
Yeah, so S is the constant of the spring,
Okay.
right? And then U is the displacement of that. So with that and this delta X is basically the force in the entire infinitesimal element. Now, of course, if we divide this by delta X, and then we take the limit as delta X goes to 0, then what we get yeah, and of course, as you know, the first term in this equation is basically our definition of the derivative. And that is our differential equation. And I'm actually going to move it here because I want to
And what is exactly the difference between U and dx?
U is a displacement. Dx is a portion of the bar. So,
yeah.
so the force that this bar is going to experience at that point is proportional to the displacement at that point.
Yeah.
Yeah.
Yeah. Okay. And
Okay.
then the longer the bar, therefore the dx is in there. Or
Yeah, dx is just a portion of the bar.
Yeah.
It's just a length.
Yeah.
So it's basically in its undeformed configuration.
Mhm.
So if you take a point, that point is going to move to the right, and that movement we call a displacement. That's why U in this case is our displacement field,
Yeah.
right? And the force that is going to experience that point is proportional to that displacement, because
Yeah.
of course it's attached to the exterior world through this spring that we call S. Yeah, clear?
So
Okay, so what we found is basically Yeah.
So B is the external force and is M then the internal force? Between B and M.
So B is going to be your is some sort of load per unit length that you apply to the bar, and well, like body forces, right? For instance, our weight, that is also a force that it could be understood by this B that we have here. Actually, that's why we're using that symbol, because normally it's used for body force, but of course it's something that is exerted on us, right? The gravity forces. This is not internal, right? Okay, so let's talk about what this axial force is. So if you remember from your previous courses, you know that the axial force is basically, can be written by the stress in the bar multiplied by the area, and then the stress through Hooke's law, right? Everybody should know this, is basically Young's modulus multiplied by the strain multiplied by A, which is the area again, and then if you remember, the definition of strain is the gradient of the displacement field. So now we have EA du dx. So when we plug this into the equilibrium equation, what we get is our differential equation now looks like that, and because of that I'm actually going to put the square on that, because that is our final version of our second order ordinary differential equation. Yeah. And of course, what we want is for that to be satisfied for every single point along the bar. So if we find a solution that satisfies this equation and the boundary conditions everywhere along that bar, then we have found the exact solution to the problem. Okay? So this has to be valid. Let me put it like this. For all x that belongs to omega, our little domain. Yeah? So how do we go about solving this equation? Well, who has an idea? Who has done this before?
Well, you have to propose one solution with exponentials, for example.
No. We don't propose solution. We find the solution. But what do we do? So we have a ordinary differential equation, second order. What do you need to do?
Well, but usually the solution for this type of differential equation is with exponentials. And what you need to know is like the values that are in the power of the exponential.
Mm-hmm.
Then you get constants, and you get those constants with the boundary condition.
Okay. We don't assume a form for the solution U. We find it, and for that we need to integrate. Right? We integrate this equation twice, and while integrating, we're going to have two constants, which is more or less what you said in the end, but we don't assume at this stage any form of the displacement field. That's what we want to find. Okay? So, and since we need to find out the two constants of integration, what is going to give us those constants of integration? The boundary conditions. Okay, so what are the two things that we can do to this bar? So there are essentially two types. Actually, there are three types of boundary conditions, but we're going to focus on two, and we're going to discuss the other one. But in this course, mostly we're going to be talking about the first type, which is called essential or Dirichlet boundary condition, right? And this is something that is imposed on the primal field or primal variable. And in this particular case, the primal field is the displacement field. We call it primal field because, well, sometimes we're working, we provide a formulation, for instance, and then that can work for heat conduction problems as well, in which case you don't want to be talking only about displacement, right? You talk about the primal field, right? So you have a primal field and then the dual field. So how do we impose that? Well, normally what we do is we say the boundary condition is U has to be equal to some function or some value in this case, right, on gamma U. And gamma U, we denote usually the part of the boundary that has prescribed essential boundary condition. So in other words, we decompose gamma. Remember how we define gamma here. Gamma is defined as the closure of the set minus the open set. So that's basically the two endpoints. And then that can be decomposed further into a portion of the boundary that has prescribed displacement field and another portion of the boundary that has prescribed traction. Okay, and that they basically take us to our second type of boundary condition, which is called natural. Mathematically, is known as Newman boundary condition, and this is on the dual field. Which in this case is our axial load. Yeah. So in this particular elasticity problem, this is the displacement. And here's the axial load. And well, what is the value of the displacement? Well, as you remember, we wrote that here. So the displacement is going to be equal to EA du dx, right? Evaluated, this expression is going to be evaluated at gamma t and multiplied by some n, some normal, is equal to some prescribed value of the force. And it is important to know that by convention we normally have so if I draw, for instance, a little picture here of a bar. Let me I'm very much into making perfect lines, as you can see, but doesn't happen with this device. Okay. So that is going to be our force P, right? And by convention, this force P is actually in the positive direction, right? So then a negative strain is actually caused by compression, right? In the bar. So therefore, our sign convention, that's why I have this this n here, because if I multiply that positive force by the normal at that location, which is negative, then I get the conventional negative compression along the bar. Okay? So in other words, this n is either -1 at the left or +1 at the right. So similarly, I could do a drawing where I fix the left side of the bar, and then I apply a force in the negative direction that is going to cause compression, but then the normal is actually going to be equal to 1 at that location. So it's exactly the same thing. Yeah?
What is the T, gamma T?
Yeah, traction. Some people call it N as Newman. I have used both in papers, gamma T, gamma N. Normally we choose gamma U for the displacement of the primal field. Yeah. Okay, finally, we have what we call a mixed or Robin boundary condition, which is just a combination of the previous two, right? It's a combination. And this can be nicely written as, well, let me just copy this. Now, of course, it's not gamma t, but we're going to change the symbol and we're going to use gamma h. So you can think of this type of boundary condition, I'm going to draw it here, as being some combination something that looks like this, and this h is the spring constant that we're going to use. So this type of Robin boundary condition is actually used a lot in heat convection problems, right? So there is sometimes heat convected to the environment through a film coefficient, and sometimes basically you have the temperature of the environment is one of the values that shows up here. That is going to be your U bar, right? And that's why I use the H notation, because normally that's the film coefficient that some people use. But essentially, it's just a mixed boundary condition. So you can think of if I increase the value of this constant, right? Well, that is going to be very, very rigid, and then this is going to be very close to a prescribed displacement field. Whereas if H is very, very small, right, that prescribed boundary condition, that essential boundary condition, is not imposed correctly. You have a question?
What is H?
H? H is our constant for that spring that we are attaching. So you can think of, the higher the coefficient of that spring, the closer it's going to be to a essential boundary condition, right?
And U bar minus, that's U over.
Yeah, this here means the restriction. So you probably have seen this in previous courses. Who has seen the restriction of a function? No? Okay, so this line here means the restriction. That basically means that you are evaluating that U, which is a displacement in our case, at that particular location. In this case, it's gamma H. Okay? Yeah? All right. So now we have basically all the ingredients to formulate the strong form of the boundary value problem. Question?
I have a question. Is there also a load in the mixed boundary condition or not?
No.
Okay.
And that is, well, essentially what you're going to see is that when we do the integration by parts, after we come up with the weak form, the boundary conditions naturally arise there, right? And then this term has to be replaced. And in the case of a Robin boundary condition, we replace it with this quantity. But we're gonna get there. Okay. So far, so good. Easy. No?
The H and the S is just like the elastic module of the spring.
Yeah, it's the elastic constant of the spring. Now, of course, you can have all sorts of combinations here, right? We can have the left end of the bar and the right end. We can have a prescribed essential boundary condition, in which case this is called a pure Dirichlet problem. We can have a force applied to the left and a force applied to the right, in which case it's called a pure Newman problem, right? Which can be solved up to a constant, because of course you're applying force here and there, and then this can, you are not restricting the rigid body movement of this bar. So you can always solve the problem. The problem is going to be singular, but you can still solve it up to a constant, because if you are interested in the stress or the strain state in the bar, you can still get it, right? But of course, it's more tricky. So it's always nicer when you prescribe the essential field somewhere to restrict the rigid body mode. And then we can still play with combinations. So you can have a Newman boundary condition here and a Robin in the other, and so on. You can make all combinations. Yeah.
You also have higher order boundary conditions, because as I see here, Newman is a derivative of like essential.
Yeah.
You also have second order.
No, because in this particular boundary value problem, our conditions are by the first derivative, right? We have to integrate twice, and therefore that is where we need to get our boundary condition. So there are other partial differential equations or ordinary differential equations that have high order derivatives. Right? I can think immediately about bending, in which case you need to prescribe some other quantities, right? But for this particular problem, it's only on the first derivative. Okay, so now we have all the ingredients to set up what we call the strong form. We're doing in time, still plenty, right? We're good. So we're going to formulate our strong form. Of the boundary value problem. And then I'm going to get a little bit more mathematical, and I'm going to say, well, given some quantities, and what are those quantities? Well, of course, we need to know what the Young's modulus is. And I'm going to use this mathematical notation that sometimes you're going to find in everywhere, right? So basically a function, E is going to be a function that goes from domain to codomain. So E has to be defined in the closure of the domain omega, and then basically it's just a real value. Yeah?
What did you write
On the right?
before the E? Yeah.
Given.
Given. Oh, sorry.
No, sorry. My handwriting is not the best, as you can see. Then we have the area that we're also going to assume that this is a function. Of course, it's a real quantity. Then we have our spring S that goes from omega to reals. Then I have our load per unit length. The same thing. Given all these quantities, what we have to do is to find U such that, and I'm going to copy this, and again, what is important is that this has to happen for all x that belong to omega, right? But that is yet not complete because we're missing the boundary conditions. And as I said, we can have any sort of combinations of boundary conditions, and we can say, well, U is equal to U bar on omega U. And then, for instance, EA du dx n is equal to n bar on omega t. And then we can have potentially another type of boundary condition. Let's say U is equal to U bar on omega U, and then EA du dx is equal to H U minus U on gamma H, and so on. Yeah, and normally, well, I have not put it here, but normally what you say is, for instance, if you have a part of the boundary that has a prescribed displacement and another part of the boundary that has a prescribed traction, normally you say, well, gamma, my boundary is basically just gamma U union gamma T. Okay, so it's basically the union of the 2 points, which for a 1D case, it's a bit tricky if you think about it, because these 2 points are very far apart from one another, but you have to think in terms of sets. Okay? And of course, we are looking at, sorry, this is a union symbol.
Oh, okay.
Yeah? But of course, we're looking at 2 points that are separated, so the concept in 1D is not so straightforward as in higher dimensions. But let's not get very mathematical here either, okay? So we'll get there when we talk about spaces, although we're not going to go into too much detail. And that's it. That is basically the strong form of the boundary value problem. Yeah? Yeah.
Just have some, like, with the boundary conditions, this is satisfied or is solved, because you have to find U such that this with boundary conditions, you have to solve it or find a solution for you.
Yeah, exactly. So now that we have formulated our problem, Now we have to solve it, right? To find our exact displacement field. And how do we do that? As I said earlier, well, we integrate the ordinary differential equation twice. Then we use the boundary conditions that we have. We plug them in to obtain those constants. And after we do that, we obtain the solution, right? And in a one-dimensional setting, this is actually pretty easy to do. It's very straightforward to do, okay? It's not so difficult, particularly if you don't have these other terms, like, for instance, if you don't have this force that is acting against the movement. In those cases, getting the exact solution in a one-dimensional setting is very easy, and it's actually also something that we do, for instance, when we are developing new formulations. We like working with exact solutions because if we have exact solutions, we can determine very easily convergence rates, for instance, right? So that's why we do this. But the problem with this is that it is very rare that in an actual problem you can determine the exact solution. The moment you go to 2 dimensions or 3 dimensions, it is nearly impossible to obtain the exact solution of a problem. Unless, of course, the geometry is very regular, you're working with a square plate or something like that. It's extremely hard to make sure that your differential equation is satisfied point-wise all over your domain. It's very difficult. And therefore, we do what? Yeah, we do finite elements, but you're getting too fast. Before that,
Weak solution.
we get a weak formulation. And what is the weak formulation? Galerkin, yeah. So, yeah, Galerkin goes further than that, but the weak statement of a problem is basically relaxing the point-wise requirement that your solution has to be satisfied everywhere in your domain. And what we're saying is, well, how about we come up with an integral form of equilibrium, in this case, so that on average, it is satisfied. It's equal to 0 in this case. So we're having an integral form of equilibrium that is satisfied on average instead of point-wise. And that is the whole point about our weak formulation. Yeah? So how do we do that? Well, let's write it down. So we have our weak or variational form. Yeah? So we know we need to satisfy this on average. Well, what do we do? Well, we copy our differential equation. Let's bring this here. And what we're going to do is we're going to weight that with some function that we call w, and we're going to integrate over the limits of the bar, over the entire bar, and then we're going to say that that is going to be equal to 0 for all functions w in some yet unknown space that we call E of omega. And this E of omega is something very interesting because we are going to choose all our test functions w from this space. And for now, we're going to just say about this space is that it should give you the space of functions that give you a finite strain energy, because it doesn't make sense that I make an integral and then finally my strain is infinite. That doesn't make any sense. So we're going to define our E to be all the functions for which this integral here is finite. And we're going to call that our energy space. Clear on that? Super, super easy. So,
what is the upper limit of the integral?
L. So you're integrating over the whole length of the bar, and the length is L. So let me maybe just better write that symbol, L. Okay? So again, mathematically, how do we write what I just said? Well, E is basically going to be defined as the set of functions V such that the strain energy that I'm going to call uppercase U, which for this bar is basically 1/2 of the integral, and then I have EA plus SP square. This is the way we define that strain energy for the bar. This is less than infinite, and by saying that, I'm saying that the strain energy is finite.
So S and what? Omega or U or V?
V, because remember I'm using V. You see? So now I'm of course I can change the symbol. If I take U from that space, then everything is changed to U. Or if I take W from that space, which we're going to do in a minute, everything is going to be in terms of W. But right now I'm defining it in terms of V. That's why I'm saying here, this is the set. So this nomenclature here, this is the way we say a set, like curly braces define a set, is the set of functions V here, such that the strain energy of that function is a finite amount. Yeah? And well, now, if we have an energy space that gives me finite value of the strain energy, you should be able to quantify that. And normally we quantify things in spaces by using a norm, right? And if you look at the Euclidean space, for instance, if you have r squared or r cubed, then we use the norm of a vector, for instance, to quantify how long that vector is, right? So you could actually say that this energy space induces the norm. And we call this, of course, since it is an energy space, we call this the energy norm. And we're going to denote it like this. And we define it to be the square root of my strain energy. So that is how we're going to measure things in this space. Now, keep in mind that there are going to be tons of analogies between spaces, function spaces, because now we're talking about function spaces, and Euclidean spaces. There are a lot of analogies, but they are completely different animals, and you have to really be careful about this, right? Because if you are in a Euclidean space, you can draw a vector, and that's going to have a length that you can quantify by a norm. But we can bring these concepts forward to a function space, and therefore we need to be careful in how we define things and how we measure things. And this is the way we are going to measure the norm of a function. Okay? So in other words, if you look at what I just wrote, I'm basically obtaining the strain energy of this function V, for which I have to integrate over the entire length of the bar. I'm going to get a value, and I'm going to get the square root of it, and that is going to be the norm of that function. Yeah? So this is a little bit more abstract than just looking at the vector and then, okay, I understand what is the length of the vector. This is a little bit more abstract, but the analogies are still there, okay? You with me? So far? Who's lost?
Can you explain the last part again, the norm?
The norm? Yeah, so if we're talking about space, right? As you have a Euclidean space and you want to measure things in a Euclidean space, so you want to know how long is a vector, for instance, right? Then we want to do something similar here, right? And what would be, how can we define the norm of a function space? Well, this is the way we do it. Okay? So we take the strain energy of a function, so we have to integrate that function as you have here. We carry out that integral, and then we take the square root, and that is going to be our norm. And we actually use this energy norm a lot, and you're going to use it when you do the project, because one of the questions that I ask you is, give me your convergence rate for the finite element method in the energy norm. And therefore you have to compute the strain energies, and you have to get the square root of that value, right? And then you're going to plot that value as a function of the mesh size. And that is going to give you a line with certain slope, and that slope is going to be your convergence rate. Right? So we're going to really not only think about in abstract terms about what the energy norm is, but practically you're going to compute this yourself, okay? All right. Okay, so let's see what we have. We still have 15 minutes. Yeah?
The question about the notation again.
Yeah.
Given E is the set of, that's a V, such that U of V equals all the stuff.
Yeah, this whole equation here means, I'm going to read it again, right? The energy space, right? Of course, it makes sense to talk about energy only along the bar, because outside the bar there is nothing. So we talk about E of omega. So the energy space is defined as the set of functions V for which the strain energy that I call uppercase U is finite.
Yes.
Yeah.
U is a function of V as well. Or did I misread it? Are they both?
U is uppercase is the symbol that I use to denote strain energy right now.
Right.
It's not the displacement lowercase u that I used before. This is strain energy.
Right.
Yeah?
But it's a function of which symbol is inside. Right?
Yeah. It's a function in this case, in this definition, it's a function of V.
V again. So it's V is the set such that the displacement function of V equals
No displacement, strain energy.
strain energy.
Again, this is the set. What is the energy space? It's the set of functions V such that the strain energy of that particular function is finite.
Right.
Yeah? Yeah. There is no lowercase u here. So in other words, actually V is your displacement field, right? That's how we compute the strain energy. Okay, how much time we have left? 0.
Yeah.
But don't we have until 15?
So 30.
Oh, okay. We don't have more time, so we're gonna. Yeah, actually, the next to finish with the weak formulation, we need more time. So in any case, I think this is a nice point to stop. There is one more question there.
Do we also require that V not equal to 0, or that okay?
V is not equal to 0.
Yeah, correct. V is
We are actually going to talk about that in the next class, because these functions have to satisfy some constraints. And actually, we want this V to be 0 at some points in our domain. And we're going to explain why. Okay? But that is for the next Tuesday. All right? I'm gonna post these lectures today in the Bright Space. So if you need to go over them, you're going to have them immediately available. Please, those of you who did not send me your username for the Nota Bene, do so, and you can immediately start reading the material there. Thank you, guys.